Welcome, everyone. I'm Dennis Irwin, Dean and Moss Professor at the Russ College of Engineering and Technology. Most of you know me. I'm honored to be here today to welcome you to this Stocker lecture featuring CHRISTOPH H. HITZENBERGER, one of the recipients of the 2017 Fritz J. and Dolores H. Russ Prize. It's our third lecture celebrating the 2017 prize. We previously hosted Eric Swanson and Dr. David Wang. The 2017 prize recognizes the invention of optical coherence tomography, or more specifically, the work of, quote, and this is the citation, leveraging creative engineering to invent imaging technology essential for preventing blindness and treating vascular and other diseases. The prize itself is a $500,000 award. You may not know this, there's no Nobel Prize for engineering, and Fritz and Dolores Russ established the Russ Prize with a gift to Ohio University with several goals. One was recognizing achievements that improve the human condition, and another was to link Ohio University to the National Academy of Engineering, which awards the prize in cooperation with us. It's currently the top bioengineering prize in the world, with just a few former accomplishments for its award, being kidney dialysis, the automated DNA sequencer, the oxygen sensor that was an enabling technology for open heart surgery, and the technology behind LASIK surgery. Now to introduce our guest, Dr. HITZENBERGER, a physicist, is vice chair of the Center for Medical Physics and Biomedical Engineering at the Medical University of Vienna. He co-founded with co-recipient Adolf Fercher the university's biomedical optics research group and developed a system for measuring interocular distances. This work led to the development of the first commercial LCI, Ocular Biometry system. That technology was expanded to record OCT images, the first in vivo retinal images of the human eye. He also demonstrated, with Dr. Fercher, the first application of spectral domain LCI to intraocular ranging, and this enabled rapid 3D imaging and revolutionized retinal diagnostics. Dr. HITZENBERGER received the award of the Hoechst Foundation? Hoechst Foundation? Hoechst Foundation. I will never get that right. And if I do, I won't get it right the second time. Foundation for Advancement of Medical Research in Austria, and he's a fellow of the International Society for Optics and Photonics and of the Optical Society. In addition to serving as editor-in-chief of Biomedical Optics Express, he's the author or co-author of some 150 peer-reviewed scientific publications. He studied physics and mathematics at the University of Vienna and received his PhD in 1983. He earned his habilitation in medical physics in 1993. Please join me in welcoming him to Ohio University.
So, good morning, or better, good afternoon, everybody. So it's a pleasure to be here. I would like to thank the University of Ohio for awarding me with the Russ Prize, for inviting me to come here and to speak here and on this occasion. So the title of my talk, From Ocular Biometry to High-Speed, High-Resolution and Multifunctional OCT, is of course related to the Russ Prize, and the subtitle here, 30 Years of Coherence Ranging and Imaging in the Human Eye, explains a bit the first half of my talk. So you probably know by now that we recently had a very important anniversary of OCT technology in 2016. When I was informed that I was awarded with the Russ Prize, we were just celebrating the 25th anniversary of OCT. So that was a very good timing, I would say, for this prize. And I should say that in the same year we had another anniversary, 30 years of partial coherence or low coherence interferometric biometry in the eye, which is the predecessor technology, or let's say the basic ranging technology of OCT. In my talk, I would like to divide that talk into two parts. One, the first half will be an historic overview from the history of OCT and its developments from our perspective, and the second part will be a demonstration of examples of current research in OCT technology. So I start with interferometric ocular biometry. And I would at first like to give tribute to this man. This is Adolf Fercher, the longtime head of our department and the second Russ Prize winner of Austria, of my department. And he unfortunately and very sadly passed away 2 weeks after the prize was awarded to him. Because of the importance of his work, so I would like to present also on his behalf at least the first half of this work, of my presentation is somehow also devoted to his work. So he made in about 1982 a first very important observation. That's the, so to say, the basic foundation of all of our work. What he did, he illuminated the eye with a laser via such a beam splitter and observed and wanted to know what happens with the light beams that come back from the eye. So he observed from this side of this beam splitter, and what he saw was an image like this. This is a large background with some speckles, and overlaid is a pattern of concentric interference fringes. Here's a zoom in. And he observed that these fringes pulsate with the heartbeat. So his interpretation of this type of image was that it is generated by light beams, by interference of light beams that are reflected at the cornea and at the retina. The beams that are reflected on the cornea have a spherical shape, a spherical wavefront, and the beams that are reflected from the retina are converted into a plane wave by the refractive optics of the eye, and the interference of a spherical and a plane wave gives such circular interference fringes. He came up with several ideas of how this observation can be used, and for the sake of time, I just go into more detail of the most important idea, and this was to use this observation, to use this effect to measure the length of the eye and of other interocular distances. So how can that be done? If you observe this pattern for a longer time, you will see that it oscillates with the heartbeat. So you can carefully measure the length changes of the eye by counting the number of interference fringes at a given point, but it is in this form not useful for any absolute measurements. So now the main idea was to switch from interferometry with a laser with a long coherence length to partial coherence or low coherence interferometry. So what is the difference? In normal interferometry, you would use a single mode laser, a very narrow bandwidth which has a very long coherence length, and the fringe oscillation, the fringe visibility or fringe contrast stays constant at 1 over no matter how of the path difference of the interfering light beams. However, if you switch from the single mode laser to a broadband light source, the fringe visibility is only given if the two paths, if the interfering beams travel the same path length. So if the path difference is 0. So only in a very short interval of path differences will there be any interference fringes observable. So he replaced or let's say he added another light source for these measurements, a multimode laser diode, which had a coherence length at that time of about 100 microns, and the fringes were normally gone. And then he added an interferometer, this Fabry-Perot interferometer, into the illuminating path. And this generates, apart from the direct beam, a copy of the direct beam that is once reflected at this plate and this plate, and now both beams illuminate the eye. Each of them is reflected at the cornea and at the retina, and observed via this infrared beam viewer. So this operates in the near infrared. Normally you wouldn't see such an interference pattern. However, if you adjust this interferometer arm length difference to be exactly equal to the optical length of the eye, then two of the beams can interfere again. The direct beam reflected at the retina and the delayed beam that is reflected at the cornea. So to measure the length of the eye, you have to move these interferometer plates until you observe these fringes, then measure that distance, and it will be equal to the length of the eye. So this is the basic idea, and this was published first or presented first at an SPIE meeting in 1986, and in more detail published in 1988. The downside was here that it was a very, very slow method. So the idea was to use it in patients, in cataract patients. For what is this used? In cataract, the opaque eye lens is replaced by an artificial intraocular plastic lens. And in order that the patients after surgery have no refractive errors, you need to very carefully measure the dimensions of the eye. So the most important distance is the length from the cornea to the retina, so that you can pick the plastic lens with the correct refractive power. So this was about at the end of the 1980s, and at that time Fercher moved from the University of Essen to the University of Vienna and formed a new group there, the group on for biomedical optics, and hired me as his first assistant professor. And his first task to me was improve this technology so that it can be used for patient imaging. This was pretty much, he didn't exactly tell me how to do it. He said I should figure out how this could work. So it was a very interesting task, and at first we thought about doing some image processing, looking for these fringes, but it was very clear to me after a short time that this would not work, because computing speed was very slow at that time, so it was clear that it wouldn't work. So I came up with another idea, and this was to replace this looking for static fringes by introducing the heterodyne interferometry here. That means moving this interferometer plate with higher speed. In that case, the delayed beam will observe a Doppler shift in its frequency. And in case of path length matching, you will have the interference fringes oscillate with the Doppler frequency, and this can easily be extracted by an additional photodetector here and a bandpass filter. And that's what we implemented, and the first hints that it works, we had that about at the end of 1988, and then improved that further and submitted the paper in early 1990, and at that time publishing was still very slow, so it took a year until the paper was published. This was published. Yeah, one of the images of the is shown here. So what do we see here? We move the interferometer plate, and at the position of path length matching, you get a signal peak. So this is just the envelope of the coherent signal. And this peak corresponds to exactly to the length of the eye. And the measurement time was immensely reduced from 15 minutes to 3 seconds by this method. This, by the way, this kind of signal is now known as an optical A scan. So this was the first optical A scan ever published. And this forms a kind of, you could say, of one-dimensional image. This is the basic scan of OCT. An OCT scan consists of several hundreds or thousands of these A scans. We quickly observed that if we arrange or align the instrument in the eye properly, we get more signal peaks. For instance, 2 peaks here, one from the anterior and from the posterior surface of the retina. So we were able to measure the thickness of the retina. And you get even some weak signals here from deeper layers like the choroid and sclera, which are somehow buried in noise because the sensitivity was not that good at this time. And we were also able to measure retinal profiles of the surface of the retina. And this data here indicate the excavation of the optic disc. So there was also already some 2-dimensional information here in this paper. Okay. In further studies, we improved the method further. We replaced the multimode laser diode by a superluminescent diode, which has a much shorter coherence length, and we're able to measure all intraocular distances with very high precision. For instance, the anterior chamber here, the corneal surfaces, the surfaces of the lens, and we did some studies on accommodation. And more interestingly, we did studies in cataract patients. And this is the result of a first comparison in 100 cataract patients with ultrasound. Ultrasound was the gold standard technology for measuring the eye length at that time. And you see that there's a very good correlation between both methods. And the interesting point was, and this was not absolutely clear from the beginning, is that it really worked in cataract patients, because you have to measure through an opaque lens, and it is not clear that that works with an optical method. But since the light wavelength is in the near infrared, the scattering is less pronounced, and this first result worked in more than 90% of the eyes. We were able to show that the optical method has a much higher precision than ultrasound, more than an order of magnitude better, and this translated into a better visual acuity of patients operated along the optical data than the ultrasound data. And this finally convinced the Carl Zeiss company to bring an instrument based on this technology on the market. Here's a modern version of that. This is one of the most successful optical imaging or optical measurement technologies that is used for ophthalmology. This instrument has been sold several 10,000 times and is now the gold standard for this application. Okay, so this was one-dimensional data acquisition. Now we go a step further from biometry to imaging, to optical coherence tomography. Since I will show several results in the eye, and I'm not sure if everyone is familiar with the details of the ocular anatomy, I show some interesting structures here at first, because you will see them later on. So here's a cross-section through the eyeball. Here is a fundus photo. This is an en face view of this area here. So this was pretty much the only imaging technology before OCT was introduced. This provides two-dimensional images. And here's a zoom in. There are two very important structures in the eye. This is the optic nerve head, where the optic nerve emerges from the eye and connects the retina with the brain. And this is the fovea centralis, the area of the sharpest vision. So any damages to either of these areas can be detrimental for vision. And here's a modern OCT image of this structure. So you can see, so here's the fovea centralis, there's the retina is a bit thinner here, and here's the optic nerve head, and you see that all the layers of the retina can be displayed here with very clear detail, and such an image can be recorded in a fraction of a second now. It was a long way to get there. So, how do we build up an OCT image? We have to record optical A scans at several adjacent positions, convert the signal intensities into grayscale values or false color values, and mount the data set to such a two-dimensional image. The first group that did that was David Wang, Eric Swanson, and Jim Fujimoto from MIT, the other winners of the Russ Prize 2017. And this is the first image they published in a retina in vitro. And you can see quite some interesting details here, the retinal surface, the thickness of the retina, the excavation of the optic disc. So here's the optic nerve. And here you can see a cross-section of a blood vessel. Here's another blood vessel. So when we saw this paper, which was published at the end of 1991, we thought, of course, we have to do that too, and we wanted then to be the first to publish in vivo data. So here is our first in vivo OCT image published in 1993, and of course, according to modern standards, the quality of the image is not very good, but you can see at least some details. The thickness of the retina can already be measured. You see the excavation of the optic disc. You see here this so-called laminar cribrosa. Imaging time was very slow at that time, minutes. In the same year, the MIT group published this image, and this, I have to say, or it was clear to us, is much better than ours was. And the main point here was that the measurement time was also much shorter. It was just about 2.5 seconds. So we thought if we want to improve on that, we have to do something very different and think about new methods to get into the front again. And now I'm coming to this topic, improving sensitivity and speed, the introduction of the Fourier domain OCT method. So this is probably the only more complicated equation that I will show, and I wouldn't explain it here in detail. This method, Fourier domain or spectral domain OCT, is based on the Fourier diffraction theorem. And this says that the amplitude of the electric field that is backscattered by the sample is proportional to the inverse Fourier transform of the sample scattering potential. So this sounds a bit complicated. What it means is that if we record our interference pattern, let's say if we record the field amplitude as a function of wave number, we can obtain the sample structure by doing a Fourier transform of this signal. So this, I explained that with 2 slides. So comparison of the older technology, time domain, partial coherence interferometry or OCT, and then the next slide, the Fourier domain version. So in time domain OCT, we have an interferometer, a broadband light source that illuminates here this beam splitter. Beam is split into a reference and a sample beam. They are reflected, combined at the photodetector, and the reference mirror is shifted, and you observe these interferometric fringes only at the position where these path lengths match, and at the peak of this position is the sample surface. And if the sample has several interfaces, you would observe several such coherent signals and signal peaks. So this is time domain OCT. Time domain because the mirror is shifted over time and the signal is recorded over time. In spectral or Fourier domain OCT, this detector, the single point detector, is replaced by a spectrometer consisting essentially of a diffraction grating, a lens, and a line scan camera. And the spectrometer, if there would be no sample, would record exactly the spectrum of the light source. However, if we have a sample here with a path difference to the reference of D, then this spectrum is overlaid with oscillations. This is a spectral interferogram. And the frequency of these oscillations is proportional to D, to this distance. So by doing a Fourier transform, we get a signal peak whose position corresponds exactly to the surface of the sample. And if the sample has several interfaces, then you would see several such peaks here. So to do an OCT imaging with that, you have an additional scanning mirror here that moves the beam to different portions, to different parts of the sample, here the retina. The reference mirror is in a fixed position, and you do such a spectral recording at every position here, do a Fourier transform at every position, and mount the data again to an OCT B-scan image. And there are two main advantages compared to time domain OCT. The first one is that there are no moving parts needed. The reference mirror can be in a fixed position. So this was our initial idea, to get rid of these moving parts, to be faster. The second advantage, and this took some time to find out, is that the shot noise is incredibly reduced by this method, by a factor 1/n. N is the number of pixels in the CCD camera. So if you use a camera with 2,000 pixels, actually you can improve the sensitivity by 3 orders of magnitude. And the combined, these two advantages combined provide for the very high sensitivity and speed of this method. So here's the first result that we obtained in 1995. This is the first measurement of an intraocular distance of the thickness of the human cornea in vivo. Here, this signal peak corresponds to the posterior surface of the cornea. Again, this is some, let's say, historic quality. This image, of course, it's still rather noisy, and the main reason is that the technology of CCD cameras was not very good at that time. They were slow and noisy and so on, but at least it worked. It took some years until better CCD technology was available that we proceeded with this technology. And here, so this, I should mention here, Rainer Leitgeb from our group. He continued the work then in about 2000, starting from 2000. And in 2002, early 2002, we were able to show some first results and present these equations that showed this sensitivity advantage. And this was now really very interesting to see this sensitivity advantage, because if you get an improvement in sensitivity by 3 orders of magnitude, this is a game changer. So we rushed into developing a complete theory of that, and in early 2003 we published this paper here that clearly demonstrates this sensitivity advantage both theoretically and experimentally. And in the same year, 2 other groups published their papers. Here, a few months later, they arrived at the same results from different ways of theoretical derivation. So this, these 3 papers then, so to say, helped us kind of to introduce this paradigm change of OCT technology. Now, several other research groups jumped onto the train. Several companies started to develop such instruments. And here is some specs of modern Fourier domain OCT imaging for the retina. The resolution, well, axial resolution is typically 5 microns, or on the order of 5 microns for commercial instruments, and for some experimental method instruments you can get down to about 2 microns. Transversal resolution of commercial instruments is about 20 microns, and if you combine that with adaptive optics, I will get to that a bit later, you can improve the transversal resolution to 2 to 3 microns, sensitivity on the order of up to 100 dB. And the speed is now commercially available, something so up to 100 kilohertz. And in experimental systems, more than 1 megahertz and even up to 40 megahertz has already been demonstrated, although these 40 megahertz systems have a lower sensitivity. Here is this slide here shows some examples of commercial OCT systems for retinal imaging. There are now more than, I think, at least a dozen companies that sell these. And here are some modern Fourier domain OCT images that are typically recorded in a few milliseconds. You get all the layers of the retinas with very crisp and sharp resolution. You can add additional contrast. For instance, here's polarization sensitive OCT, where you can generate specific contrast for individual tissues. You can do 3D imaging. Here's a volume rendering of a 3D polarization sensitive OCT data set. So to summarize this part of my talk, I should say that Fourier domain OCT technology is again one of the most successful imaging biomedical imaging technologies. There have been several 10,000s of these instruments are installed worldwide, and this has completely changed retinal diagnostics in the last decade. Okay, so I'm getting now to the second part of my presentation, and I show you some examples of current research on OCT, and I cover here improvement of resolution and some functional extensions. Of course, there are several more interesting developments that I don't have the time to cover here. So I start with high resolution, OCT combined with adaptive optics. So normally, so what we want to achieve here is to improve the transverse resolution. Normally, if you do that in optics, you would go to beams with higher numerical aperture, or systems with higher numerical aperture. You need larger beam diameters. The problem with the eye is that the optics of the eye is not very good. So if you go to larger beam diameter, then the aberrations of the ocular surfaces generate actually wavefront distortions that make the resolution worse than if you just use a small beam diameter. This can be solved by using adaptive optics. This is a method borrowed from astronomy, where it was first introduced to image stars through the turbulent atmosphere. So what is done here is, ideally a beam coming from a point on the retina should have a plane wavefront here. The ocular aberrations, however, distorted, and we have an aberrated wavefront. This aberrated wavefront can be measured by a wavefront sensor, and the signal used to control an adaptive mirror. That means a mirror with a deformable surface. And this deformable surface is shaped into a way that exactly counteracts this wavefront aberration. And so we have here again a corrected wavefront, a plane wavefront, and with this we can now achieve the full resolution that is theoretically possible. The first of these instruments were very large. They typically cover the whole optical table. There were several, let's say, parabolic mirrors used here in this sample arm. I don't go into details of this is from Robert Zawadzki from UC Davis. Robert Zawadzki was also a PhD student in our group. But if you use an instrument like that, you can zoom into the retina and get images like this, where you see these white dots, these tiny dots here. Each of these dots corresponds to a cone photoreceptor. So you can resolve single cells here on the retinal surface, and they get denser and denser the closer you get to the fovea centralis. This here is from our group, an image where you see here it's some periphery, the wider separation of the photoreceptors, and here in the center they are really extremely narrow, and this is to demonstrate the resolution of the photoreceptors exactly in the fovea is only very few groups in the world are presently able to do that. Here's an interesting, so to say, sequence of improvements that can be made in adaptive optics with additional large bandwidth, so that to improve the resolution both in the transverse and in the axial distance. Here again from Robert Zawadzki. So this here has normal axial resolution as it would have a commercial instrument, but adaptive optics. Each of these bright dots here corresponds to an interface within a cone photoreceptor. If you improve the bandwidth, you see that these structures get, so these dots get thinner or in the vertical direction, and if you use a so-called achromatic correction, you can really get to very narrow and tiny structures, and get some signals from within the individual photoreceptors. This slide here images the rod photoreceptor and the cone photoreceptor. So in the periphery you have two types of photoreceptors. The cones are used for color vision and bright light, and the rods are used for dark light conditions. And the rods are a bit longer than the cones, so you can separate them if you place your coherence gate. This is an en face view. Once within the cones, and this image here was taken where the coherence plane is at the position beyond the end tips of the cones. So you can separate the cones and the rods here, and if we combine these images, you very nicely see the cones here as red dots surrounded by the very thin and tiny rod photoreceptors here in green. Okay, now let's come to the next topic, OCT angiography and blood flow measurements. This is based on the Doppler effect, Doppler OCT. So if the light is backscattered by a moving particle, for instance a red blood cell moving in a vessel, the frequency of the light beam is shifted, the phase of the light beam is changed from one A scan to the next. And this can be measured and used to generate a vessel contrast and also to quantify blood flow. Rainer Leitgeb from our department was the first to publish a high-speed Doppler OCT image. What you see here, already in 2003, shortly after the discovery of the sensitivity advantage of this method. This is a B-scan, an intensity image, and here you see a magnification of the Doppler image. And the color coding here means that red is flow into the plane and blue is flow out of the plane. So you can identify the direction of the motion, and you can also quantify the flow speed. For instance, you see here the parabolic velocity profiles through these two vessels. This method can be used for angiography, that means for displaying vessels contrast. The first group that did this was Yoshiaki Yasuno's group from Tsukuba University. They introduced the term OCT angiography, and they were able to image the vessels in different layers of the ocular fundus. So here in the anterior layers of the retina, and this corresponds to this part, and here in the choroid. And you can combine these images and color code them, so the color means the depth. So this was the first image, and since this is a very interesting technology, several ocular diseases change the blood flow and lead to changes in the vessel pattern. There's intense research going on that, and here you see a modern version of such an image from Ricky Wang's group at the University of Washington in cooperation with SAIS. And this image really shows in very great detail large retinal vessels and the tiny capillaries, and the color coding means the depth in which the vessels are. This is now commercially available, this technology. Current research here that is ongoing is to combine that with adaptive optics. Here again a result from our group, where you can further improve the resolution of the vessels and better define the depth of the plane in which this image was taken. OCT angiography provides vessel contrast, but it does not allow quantitative measurement of blood flow. So we are presently developing a method that allows such quantification. The problem here is that if you use a single beam, a single measurement beam, the Doppler effect, or the speed that you measure just the velocity component that is parallel to the sampling beam. So to get an absolute velocity vector, at the absolute blood flow velocity, you need to get the three components of the velocity vector. So you can do that by illuminating the samples with 3 beams simultaneously, get 3 velocity vector components, and from that measure the absolute flow. This is illustrated here. So this is the final imaging lens. 3 beams are focused onto our blood vessel. We get 3 components of the velocity vector, put them into an equation with a system of 3 equations. We can retrieve the absolute flow vector. The instrument is quite complicated. It consists of 3 subsystems, combines 3 OCT systems with a joint sample arm that illuminates the eye at from three different angles, the retina from 3 different angles. And if we do a circular scan around the optic nerve head, which means, so why a circular scan around the optic nerve head? All of the vessels that provide the blood supply of the retina emerge through the optic nerve head. So if you measure the flow through all these individual vessels, you can measure the entire flow through the retina. So we do a circular scan, measure the velocity within each of these 12 vessels. For each one we get such a parabolic velocity profile, and then add all the flows through the veins or all the flows through the arteries, and obtain an absolute flow here through the retina, in this case of 47.6 microliters per minute. And the inflow and outflow is the same within the precision of the method. So here is a comparison of flow through the veins and the arteries in 20 healthy volunteers, and you see that the results are equal, which is of course expected for healthy eyes, but it demonstrates that the method works. And here's, this slide here indicates for what that might be interesting. Here's a comparison with measurements in glaucoma patients, and you see that they have a considerably lower blood flow. So this might be an interesting method for early diagnosis or for monitoring of glaucoma. So the final topic that I will present here is polarization sensitive OCT. Why are we interested in that? Well, the conventional OCT gets its images based on backscattered intensity, which works well in many cases, but it has one major problem. It does not allow a direct differentiation of tissues. On the other hand, there are several layers in the retina that can change the polarization state. and therefore provide tissue-specific contrast and be used to segment different tissues. So there are two effects that can be used here. There's birefringence, which means that the speed of light is different for two orthogonal polarization states. This leads to a phase retardation between two such beams after transiting a layer of tissue that can be measured. Examples are the cornea, the sclera, and the retinal nerve fiber layer. And there are depolarizing tissues, and the main tissue of interest is the retinal pigment epithelium, the posterior boundary of the retina. And the other tissues essentially maintain the polarization state. So a PSOCT system has some additional polarizing components here, a polarizer, quarter wave plates, a polarizing beam splitter, a second detector, so that we can measure the horizontal and the vertical polarization state in parallel. And from these data, from these measurements, we can retrieve 3 data sets. One each for the amplitude of the horizontal and the vertical channel, and one for the phase difference. And from these data, we can retrieve birefringence and depolarization information. And for sake of time, I showed you just an example of how depolarization can be measured and quantified and used. We introduced a quantity here that is we call degree of polarization uniformity. How do we analyze that? We place a tiny evaluation window or kernel in our image, measure the polarization state within each pixel of this window here, and analyze how uniformly distributed, or is there a well-defined distribution of polarization states, or are they randomly distributed? And this can be shown by this Stokes vector analysis. I don't have the time to explain that in more detail, but you can see here that in a tissue that maintains the polarization state, there are well-defined distributions of Stokes vector elements, and in a depolarizing tissue, they are more or less randomly distributed. And we calculate this so-called topo value and do that for every position, slide this evaluation kernel through the entire image and obtain this so-called topo image that shows areas of of well-defined polarization state in red or orange. Topo is high here, close to 1, and depolarizing tissue in green or blue colors. And there's only, as you see here, only one layer in this healthy eye that depolarizes the backscattered light, and this is the retinal pigment epithelium, which we can now extract by a thresholding algorithm. So why is this of interest? Well, our clinical cooperation partners were very excited when they saw that first. The retinal pigment epithelium plays a decisive role in the metabolism of the photoreceptors. If the RPE gets damaged, the photoreceptors get damaged, and this leads to blindness. And this is exactly what happens in age-related macular degeneration, which is the most frequent cause of blindness in the industrialized world. So they were interested to analyze that and to analyze the RPE and its lesions. So we developed an algorithm that segments Druze. These are an early form of AMD. These are these buckles in the RPE here. Beneath them there is some debris of the metabolism that is not removed as it should be. So the algorithm generates some segmentation layers. The red layer is the position where the RPE is actually. This is found by this depolarization method. The green layer is where the RPE should ideally be. The difference between them is the Druze. We can now calculate this type of Druze map from which we can measure the area and the volume of the Druze. And we did studies over several years, followed larger number of patients over up to 5 years, and wanted to see if there's some specific patterns of how these drusen develop over time, and we found a very characteristic pattern. It sees a slow growth of the drusen volume until a certain time point. Then we have a regression where the drusen there's a collapse of drusen, and shortly thereafter there is a frequently development of so-called geographic atrophy, which is a late stage of AMD where a hole forms in a large hole forms in the RPE, which then grows and grows and leads to an increased amount of blindness, reduction of vision, and finally blindness. We also found other interesting biomarkers that are high risk factors. Some of them are illustrated here, for instance, thickening of the RPE, these tiny holes or particles of the RPE moving into places where they shouldn't be, or this type of so-called pseudodrusen, where the drusenoid material is above the RPE. And we did some statistical analysis and found 3 biomarkers that are high risk factors, with the highest risk being pseudodrusen. Patients with these have a more than 4 times higher risk of developing late stage AMD than patients that don't have them. Okay, so I'm coming to an end of my talk, and as a summary, I decided not to summarize everything, but just to show you performance development of OCT in the last 30 years. And I decided to use as a figure of merit the product of the speed, the A scan rate, the sensitivity, and the inverse resolution. And if I say in 1986 this product equals a figure of merit of 1, then we have seen over the following 30 years an improvement of that by 14 orders of magnitude. And I think this is quite extraordinary, and few technologies have seen such an improvement in their performance over the years. And since images say more than words, I just want to conclude by comparing our first image of 1993 with a modern scan, or let's see, it's already 5 years old, 20 years later, of a retina, and I think the images speak for themselves. And here are some additional information that we get that we didn't have at that time, for instance, this polarization contrast. Okay, finally, I would like to acknowledge several people in our department, our cooperation partners in the Department of Ophthalmology, other international cooperation partners, and some of our funding sources. Thank you.
I saw. Okay. Part of the Doppler OCT, you can recover the velocities of the blood flow. Do you have the need of reconstruct the blood vessels? The reason I ask this is for MRI, we have this something called the diffusion tensor MRI, which is we take the images from different angles, and from there we can reconstruct we can get the flow of the water, and then from the velocity, just like in the Doppler OCT, we can reconstruct the fibers. I'm wondering, do you have the similar kind of necessity of doing that, reconstruction of blood vessels?
There is work on reconstructing the blood vessels or the capillaries, and the research groups that do that, they typically at first do some skeletonizing of these blood vessels and some of them then do more detailed, let's say, analysis of the structure. I would say, yes, this is of interest. There are some diseases where in some areas there is a loss of vessels. Sometimes in some areas the shape of the curvature changes, the tortuosity changes. An interesting application, for instance, is diabetic retinopathy, where there are areas in the retina where there is a severe loss of capillaries, and yeah, I would say this is certainly interesting. Yeah.
Okay, thank you. The second question is for the segmentations you mentioned. Do you have this in your institution? Do you have this manually annotated ground truths? So then, I mean, the reason I ask this, then you can do machine learning based solutions that come up with automatic solutions for the text.
Yes, for instance, what we did and what I didn't show here is this, as an example for this Druze segmentation method. We did comparison studies with manually segmented Druze and with automatically segmented Druze. And we published that, and this is a very important step to convince people that our method works, is that we can show that it produces the same results as the manually segmented lesions. We also have did similar work by segmenting geographic atrophies, where we measure the area of these atrophies and compared that with manually segmented atrophies, also with other imaging technologies, for instance, manual segmentation in fundus photos or in scanning laser ophthalmoscope images. And in addition to this work, there is a research group in our department that is located in the reading center of the Department of Ophthalmology, and they do an enormous amount of manual segmentation from normal OCT data. That means from commercial machines that do not have such, let's say, polarization sensitive add-ons. And yeah, there's lots of experience and knowledge in this group.
Thank you.
Time for one more question.
I appreciate you coming and giving the talk. I think it's very good for our students. I actually run a biomedical engineering program, and we have many of our students here today. I was wondering, clearly you've had a lot of success, your team has had a lot of success. What would you say are the... I didn't do that. I guess they don't want to hear the question.
But you can still talk.
Yeah. So what would you say are the 2 or 3 things that contributed to the high level of success you had as you went through your career that you might advise these students to follow?
Yeah, that's an interesting question, and I thought about that many times. One, of course, was to be, let's say, to be in a new field in the earliest stage as possible, when nobody knows that this field will exist, but this is something that you cannot plan. So my approach was, when I finished my study, so I came from a different field. I first worked in solid state physics. I did electron microscopy in metal crystals, which is certainly was something very different, and then was a postdoc for 4 years in this field. And after some time, I had the impression I have to do something different, and I was looking for a new field that sounded interesting to me. And then I saw that the position was announced at the Department of Medical Physics with the new field of measuring let's say, of applying lasers to ocular problems. So it was very general, and I thought that sounds very interesting. I don't have any idea about that. I went into the library, got all the literature that was available, which was not very much at that time, and then I applied for this position, was interviewed by Fercher, and I was obviously the one who was best prepared for this interview, and he hired me. So my advice would be, if you apply for a position in a new field, really demonstrate that you are interested by reading the stuff that these people have published and getting yourself familiarized with that. I think that was one of the, yeah.
Thank you.
I'm going to follow up on that. The interdisciplinarity here is what made it work, right? Fourier transforms came out of your training as a physicist,
Yes.
correct, right? And normally you would not see that if you were just studying the eye and the structures of the eye. So never stop learning and learn as broadly as you can. So thank you, Dr. HITZENBERGER. We appreciate you coming.
Thank you.